Okay, so hi, I'm Benjamin. I'm a PhD student from Edinburgh, and I would like to talk about constraint simulations of crystal balls and filaments from the caustic-skeleton model. This work is done in collaboration with my advisor Jörg Feldbauer, with Maya Rodriguez and Trien van der Becher. And in this project, we're aiming to give a more rigorous definition and identify the dynamical origin of structural elements that make up the cosmic web. So let me start by discussing the multi-streaming nature of the large-scale structure. On this slide, you can see three visualizations of a slice of the cosmic web as arising in a generic dark matter-only n-body simulation. So the upper panel shows you the density field, which clearly reveals this intricate geometric pattern that we call the cosmic web. In the second panel, you can see that this cosmic web is formed from particle mesh folding over into multi-stream regions. So these multi-stream regions, we've heard this term before, and they arise when particles from different initial positions, say here and here, they undergo shell crossing, they stream into the same final configuration here. And this multi-streaming nature is summarized succinctly in the lower panel, in the number of streams fields, which counts how many streams stream into a final position. And so what you can see in the lower panel is that the overdense structure that we call the cosmic web is an inherent multi-streaming structure that's distinct from the cosmic background. So this is suitably illustrated also in the 2D particle mesh simulation, where here you can see that the inhomogeneities grow due to gravitational attraction. At some point, shell crossing occurs, particle trajectories cross, and you form this web-like pattern. And if I were to draw the density field to that, then you would see that this is exactly what traces out the overdense cosmic web. And this is exactly where the caustic skeleton formalism comes in, because these particle mesh foldings are classified by a hierarchy of caustics, and throughout this talk, we can assume caustics to be synonymous to foldings. This is a mathematically rigorous and completely general formalism that is derived from catastrophe theory and goes back conceptually to Arnold, Darin, and Zeldovich from 1982. However, the caustic skeleton model really unleashes its physical power when you calculate it not in all generality, but in an analytical approximation, in particular in Zeldovich approximation. In 2018, Feldbauer and al. Obtained this exhaustive list of caustic conditions that classify all the structures appearing in a 3+1 dimensional universe. So I don't want to read them out, you can read them here. The important thing about them is that these are a set of nonlinear algebraic conditions on the eigenvalue and eigenvector fields of the tidal tensor. And as such, you can evaluate them in the primordial fields, and they give you the full hierarchy of multi-stream regions, which are bisected by cusp sheets that give you the cosmic walls. The cosmic walls in turn fold into filaments, and the filaments in turn fold into clusters. This formalism is fully free of any numerical parameters, and it just has two physical parameters. So for the first one, you're rarely interested in all the structure that forms in an n-body simulation. You would like to identify the structure that exceeds a certain size, such as 1 megaparsec. You can achieve that by smoothing the primordial fields and identifying caustics. And the second one is just about the formation time, the growing mode BC of the caustics. We are typically interested in those caustics that have formed up to now. You can see these two parameters in action here. So on the upper panel, I'm showing the scale space nature of the caustic skeleton, where from the right to the left, I'm evaluating the caustics on an increasingly lower smoothing scale. And so we are recovering more and more of the structure that we see in the sky. And if we are now evaluating caustics only on a small scale, but not only the caustics that have formed up to now, but also those that will form in the future, then you can very clearly see here that we are covering virtually the entirety of the structure that we see on the sky. So this plot is really convincing us this caustic skeleton formalism is something very, very fundamental. The caustics are pivotal in understanding large-scale structure. And what is very surprising is we are calculating the caustics in the Zeldovich approximation, and yet they are so good, so much better than we had originally anticipated. Just a side note on that, this multi-streaming nature of the large-scale structure is also relevant to an equation that you may remember from your cosmology textbooks. When you want to evaluate density fields from an n-body simulation, to be exact, you would have to evaluate this weighted sum over all streams that flow into a final matter configuration. We have recently implemented the phase-based DTFE method, which combines DTFE with previously proposed phase-based estimators, such as by Oliver Hahn, for example. And the phase-based DTFE JL is a publicly registered Julia package. It's stable and efficient. It's well documented. It even has a logo, and as you can see, it's also much better than the DTFE method. So if you're interested, do check that out. Yeah, I want to focus on the caustic skeleton constraint simulations. So what we want to do is, now that we know that these caustics are good at identifying the structure, we actually want to use them to set up a laboratory for large-scale structure by running constraint simulations on the caustic conditions to infer the physical properties of walls, filaments, etc. But we have a problem with that because unfortunately the naive caustic conditions fail for this purpose. The reason is that if you want to simulate a filament, say, and you take a generic point on the filament from the filament caustic condition, then this point is biased towards the clusters which absorb the matter. So what we really need is the maximum stretch point within that filament. Or if we want to simulate cosmic walls, the maximal stretch point within the walls. I'm not showing any mathematics here, but these maximum stretch points are the big conceptual new thing of our forthcoming papers, and they form the cornerstone of our constraint simulations. We then have a somewhat technical recipe for implementing these. So first, we translate the condition from the eigenfields of the tidal tensor into a condition on the Taylor expansion of the potential around the constraint point. Within the constraint manifold of all possible Taylor expansions, we then sample one random realization that gives us essentially the local morphology of our object, for example, one random wall realization. We then impose this constraint into a random field to connect it to a global random cosmic web. And finally, because we know the algebra of all these objects, we can also orient them very exactly. And yeah, so this was abstract and this was a lot of words, but I just would like to demonstrate how well this works with this constraint simulation of a cosmic wall. So here you can see that if we run this constraint simulation on a new maximal stretch condition within the wall, then we get this perfectly aligned object that is traced by the red cusp sheet. This is a random wall that's connected to a cosmic web interspersed by filaments, and it's a moderate overdensity, which you can see if you plot the slices to that object. And here in this visualization, you can also see that the density field agrees perfectly with the particle mesh, and the number of streams field again shows that this is a multi-stream region. So this is nice. We have now simulated one cosmic wall, one random cosmic wall, and physically realistic cosmic wall. We can now also simulate hundreds of them, and this is what we did. And so we inferred the mean fields. And what we find, for example, is that the cosmic walls are 2 to 5 times as dense as the cosmic background, which is well in agreement with the literature. We also obtain this dipolar velocity field, and yeah, we are commenting more on the physical properties in the papers. In the coming months, we repeat this analysis primarily for the cosmic filaments. I've already mentioned that we have two types of these, the swallowtails and the umbilicus. The swallowtail filaments are the early type filaments, which are less massive, more elongated, and they're typically found bounding cosmic walls or interspersing cosmic walls. Whereas the umbilicus, they form at late times, they are more massive, less elongated, but they are very, very special objects because they have a beautiful threefold symmetry of 3 incoming walls. And so these simulations are a bit older, so they're not as nice, but this is a simulation of a swallowtail, which arises as a folding within the red cusp sheet that makes up a cosmic wall. And this is a simulation of an umbilic. Here, this is a very fat overdensity, which you could see if it weren't for that green line over there. What you can see is the 3 incoming red cusp walls. And so just to point out, this also works for the filament, and we are working on this. That's actually what I wanted to say on the constraint simulations. Up to this point, I've been talking about particle mesh foldings and dark matter and everything, and we may now argue that this is a neat little mathematical treatment, but that this is not actually what we see in the sky, because what we're seeing is galaxies. And so the caustic skeleton is really fundamental in shaping the large-scale structure. It is the thing that makes up large-scale structure. And so we expect that caustics also have a very fundamental influence on the halo properties, and we started investigating this in a series of projects. I would like to show one particular thing that we have investigated within the constraint simulations of cosmic walls. So this is from the suite of high-resolution simulations, and these are 3 random wall realizations. The plots are a little bit difficult to read at first, maybe, but what they are showing you is a slice to the density field of the wall along the face of the wall, along with the halo positions from a thin strip around that slice projected into that plane. And on the right side, you always have the matching caustic skeleton slice, or projection of a thin layer of the caustic skeleton with the halos. And what you can see is that the halo positions are actually traced by small-scale filamentary caustics within the large-scale wall that we set up from the cusp caustic. So This is a very important observation. The halos are not randomly distributed within cosmic wars, but instead they are traced by small-scale filamentary caustic from the caustic skeleton. Moreover, the masses of the halos are not uniform, but less massive halos reside in less pronounced, smaller scale filamentary caustics, whereas the more massive halos reside in the dense clusters and dense filaments. This mass dependence of halos with cosmic web environments is not completely unknown in the literature, but has been explored before. However, for the first time now with the caustic skeleton, we can give a theoretical foundation for why we observe this filamentary halo. This filamentary halo pattern and how it is that the smaller scale halos are found within larger scale wars, for example. And yeah, this is all I wanted to say, and I'm not sure if I have time to read out the conclusion. I would just like to point out that from all of that, something that we are currently working on and I'm very excited about in the future is that we are evaluating the caustics also of our local universe. So on Monday, Tuesday, we had this talk on the dominant voids. And we would like to repeat this analysis with the dominant caustics and see what this reveals for our last structure. Thank you. Thank you.
Question?
Very interesting. And so one long-standing question is whether galaxy properties in the end are different. Did you look at anything beyond mass?
So currently we are with our collaborator in Argentina. We are investigating halo alignments, and we've also made some interesting observations about cosmic breakups, where you would, if you change halo positions along these filamentary constraints, you would manage to break apart large mass halos into smaller mass halos. We expect they have an influence also on the alignment of the halos within that, but we are not doing anything with baryons at the moment. But hopefully, maybe we can get us.
I mean, more like I guess alignment is shape and spin, but then concentration, for example. No. So we can talk about it. Sure.
Any other question?
I'm sure that it's a great idea to use the post-trade simulations for the walls, but I'm just not sure that the Lonely tessellation is the right.
The Lonely tessellation. What is it? What is not good about it?
Yeah,
the code that I was showing. So
right, okay, we can discuss it.
yeah.
Something else? Okay, if not, let's thank the speaker again.